Hello, hello. Here we go. All right. Hello. Did I see? Oh, hello, Vincent. Certainly, hello, Vincent. Vincent is I mean, he should be the receptionist in the waiting room. That's awesome. But hello, and I mean, good morning, Melanie. Yes, awesome. Good morning, Melanie. You are super prompt. Also, good morning, Gene. Thank you. And we've got the animated Avatar show going. It's like the Muppet Show, which you might have noticed you're now getting extra points for, or there's a new portal for that. So, good morning, Annie. Good morning, Vicky. Morning, Vincent. And I mean, and I tested him. Like, I understand that you could actually, it is very clever because, of course, you could walk away and it's still there, but it doesn't move as much. Like, at least it is better than it's definitely, you know. Um, anyway, I love him. So good morning, Vicky. If I didn't say, I did say yes. Oh wait. Oh, okay, okay, direct chat person. Wow, that is super honest. Direct chat person. I think there should be a portal for that. But okay, okay. So let's get. But also, why is my display? We should get going. Why is my sign my? Oh, that's weird. Okay. Okay. And did I say good morning, Amelia? Um, I feel like is this class getting smaller and smaller? Something seems to be happening with attendance in this class. A funny time for that to happen. Those of you who are here, I mean, I, I feel like people are starting to not come, and this is a weird time of year for them to do that because, as you guys know, like we're about to have an exam. This would be a good time to be in class, I would think. But of course, you know that because you're here. So why am I telling you? All right. Um, Here's what we're gonna do. And good morning, Hudson. Okay, I mean, I guess I just want to get straight to it. Like, so as I think you know, the midterm exam will be, excuse me, the real thing will be posted this Thursday evening. Unfortunately, in a conflict with Halloween, it is what it is. And then we'll be due back next Monday, right? As you also know, the way to study for this exam, the way to prepare is to try to do the practice exam that's already posted in Google Classroom. Now that's very long. I mean, I looked at it again. I have it, it's very long. That's why it's great practice. Like your exam will not be as long as that. Your exam will be taken from that. That is, there will be nothing on your exam that isn't somewhere in that practice exam. There will be nothing in your like no big question in your exam that isn't somewhere in that practice exam, but that doesn't mean that everything in that practice exam will be on your exam, if that makes sense. So it is fair to believe if you really can do that practice exam inside and out, if you know how to work it through everything, then you're set for Thursday night. Now you may not be at that point yet. In fact, I would imagine you wouldn't be. But yeah, that's your guide is to try to figure out everything in that practice exam. Now, and again, you can find old videos of mine where I walk through various aspects of it. That's all fair game. But good morning, Hudson. Thank you. Good morning. What I'm going to do today is I'm going to do one of the problems like right now, like to keep going. I want to keep going with our material, but I want to do it in a way that helps you know how to prepare for the exam. So two things. One, today and when today is yeah, today and Wednesday, if you have questions about the practice document, specific questions, the more specific, the better. I will try to answer them, or at least I'll tell you if I can't or whatever. And the more specific the question, the more focused the question, the quicker I can answer it, and the more of them I can answer over the next 2 days. Okay. Thank you, direct chat person. I love the honesty. Um, so I can answer questions and whether they're in chat or if I can say that I can say that I can't answer, whatever. But what I want to do that I think would be very helpful to you, like um what we did on last class, we learned how to add displacement vectors together. I mean, we did one example And that example could be reiterated. That is, we added two displacement vectors together. You could add as many as you want by that method, and it still works. But what I kept saying then was that the method for adding displacement vectors is a really important method to know, because it is the same, it works for adding together any kind of vectors. It's just easiest to picture and see right away with displacement vectors. Why? Because when you draw a displacement arrow, the length of the arrow, let me back up for a second. The length of any vector arrow always represents the magnitude of the vector quantity. Like for any vector, that is true. The length of the vector arrow represents the magnitude of the vector quantity. In the case of displacement vectors, it's kind of a straightforward representation, because the length of the displacement arrow represents the magnitude of displacement in space. So the length of the vector arrow actually does represent an actual length, like an actual span of space in real space. So the representation is it's almost not even basically a displacement arrow. Like you could draw a displacement arrow that's 1 inch long, and that would represent a distance of, let's say, 1 meter or 1 mile. So really, your brain doesn't have to do much abstraction. Your brain just has to scale up or scale down from the size of the arrow to the size of the kind of length that you're talking about in space. That's why hence we start all of our vector work with that lab 3, where you're literally using arrows to represent distances in geographic space. Okay. What I'm trying to get at, what I will get concretely to in a moment, is that, okay, whatever methods that we use to add together displacement vectors also work the same way for adding together velocity vectors. However, as I'm sort of trying to indicate right here on this picture, on the board, you add together velocity vectors by the same computational and graphical method. Hold on, let me just add. But what it means, what you're physically doing when you add together velocity vectors, is a little bit more abstract. It's a little bit more conceptually challenging. So what we're going to do in a minute is we're going to walk through a big addition of velocity vector problem. There were a number of them that were assigned in the homework 7 spatial relations homework. Like, in fact, a big purpose of homework 7, which is a very long homework, and many of you have done a first draft and you've gotten many points. And then as you learn more from what I'm going to say today, you can revise and get more points, yada, yada. But the thing about homework 7 space relations is that a lot of the stuff that you're doing there is trying to build up all these concepts that I'm now doing somewhat quickly in class, like building up the concept of a displacement vector, first in 1D space, then in 2D space. Then it builds up a velocity vector in 1D space, and then in 2D space. And eventually it's trying to get you to see what it would be like to add together two-dimensional velocity vectors. Specifically, I mean, like on the second to last page of homework 7, when it's talking about an Audi and a Buick and a highway or an interstate. And it talks about the Audi's velocity relative to the Buick and the Buick's velocity relative to the interstate. And they're going off at different angles. Like by the time you get to the end of a very long homework 7, like the second to last page, you're now trying to relate velocities of different objects that are going in different directions within the plane of two-dimensional space. It's very hard, in other words, but you have to do a lot of work even to get to that point to see it. What's happening by the end of homework 7 space relations is that you're being asked to both compute and conceptually understand the addition of velocity vectors in 2 dimensions. Now, okay, it's like a summary. Now, the concepts are, crystallized right here in this board. What I'm about to tell you, what I want to tell you is, the course, as I warned you, like the course gets sort of faster and faster as we go. We spend a lot of time building up the fundamentals at the beginning, and now we're trying to just apply those fundamentals like at a faster and faster pace. So what I'm going to do now that exam's coming up, instead of me walking through all these examples of homework 7 as you already attempted on your own, instead of me walking through all the examples and getting to the big final purpose of it, which is like the Audi and Buick going at different directions in space, I'm going to jump to the chase, cut to the chase, because I think all of you will appreciate it more and benefit more. I'm going to go straight to the two-dimensional velocity vector addition problem in your practice exam. And I'm going to walk through it right now. So I'm going to say one more time. So I'm going to do that. In fact, I'm going to post. So I'm going to let me screen share. So I'm going to show you what we're about to do. What we're about to do. Is this it? Yes, yes, yes. Yes. Okay. Okay, so just briefly so you can see. So here, so you may have looked at this already, you may not have. But right here on page 6 of your practice exam, it's talking about velocity vectors in 2 dimensions, and there's a problem on page 6 called free float, which is really just another version of the Toyota and the Pontiac. Was it Toyota? I thought it was Audi. Whatever. Toyota and Pontiac problem on like the second to last page of homework 7. Now, again, and I'm going to jump straight to this and walk you through it and show you how to solve and show you what's going on. Now, again, those of you who like lots of different practice, if you like practicing lots of different things, exercises and variations before an exam, like I would suggest that on your own, after I do this, go back and look at the problems from the homework and practice them and see, if you're doing any better on them based on what I say here. But those of you who just want to get like straight to it and like prepare for your exam, I'm about to give you one of the solutions. Okay, now again, I'm not promising that I'm giving you all the solutions in class time before you take, but you can find the old ones on videos, etc. But I think this one is this is a big one, and it's very relevant. It picks up right from where we left off the material last class. So anyway, what I'm going to walk through is this problem here in page 6 of the practice exam. Again, this is a problem in adding velocity vectors together. Last thing, sorry, all this introduction. This is a problem in adding velocity vectors. Just like last class, we added together displacement vectors. Now we're going to use the same method to see what it means when we add velocity vectors. But also, for those of you who weeks ago, when you watch the video on Galileo's principle of relativity form number 4, and you wrote to me things like, okay, I sort of get what you're saying with form number 4, but I don't like really see how we would apply that in a problem, or can you give me concrete examples? Well, here we go. This whole exercise in adding velocity vectors, or this whole topic, is a direct and concrete application of Galileo's principle form number 4, the mathematical one, the one VAA equals VAA, VAB equals negative VBA, VAC equals VAB plus VBC. That business, that's what's going to happen right now as we go over this. So, I'm just looking if there's anything in the chat. So this is what we're going over. If you want to screenshot it or whatever, we may not, I think we'll finish the whole thing today. We may not do anything but this today, but okay. Anyway, that's what we're doing. Let me stop the share, stop the madness, go back to the other share. Oh, is there anything in the chat? You're back. Okay. All right. And what you see on the board here is an overview of the method. Like basically just quickly, just notice on this front page, this is just in general what it means to add velocity vectors. Notice the middle picture when you the middle picture is just like what we said on Monday. When you add, and you may want to write this in your notes or whatever, just remember one key point. When you place vectors tip to tail, you are adding those vectors, whatever they mean. You place the tail of one vector next to the tip of another vector, then whatever third vector completes the triangle formed by them is the answer to the addition problem represented by both of those vectors. Okay, that's point number one. Point number two, I should say quickly. So again, if you're just looking at the middle picture on the board here, each one of those arrows, like VAB, VAC, VAC. Oh, sorry. Oh, thank you for, wait, that's a, hold on. That's supposed to say VC. Okay, sorry. I hope, I almost feel like, wait, can you just raise your hand quickly? Can you just raise your hand, electronic hand quickly, if you just caught that I just corrected an error on that picture? Like, I want to make sure you, like, there was an error on the picture and I just corrected it. Can you raise your hand if you acknowledge that, or if you catch, should I do it again? Like, just please note, it says VAB plus VBC equals VAC. Now, thank you, Annie. All right, that's good enough for me. And thank you, Hudson. Thank you. That's good enough for me. All right. So Hudson and Annie are ready to take this exam. Okay. No, I'm just kidding. No, thank you guys. Okay. So the other thing I have to quickly say before I get rolling on this, notice each one of those arrows in that picture is supposed to be a velocity vector. Note now, though, that means, like, this is a little bit more abstract. That means the size, well, the direction of each arrow, the orientation of each arrow represents the direction of velocity in two-dimensional space. But the size of the arrow represents magnitude of vector in two-dimensional space. So that means that the longer arrow, like that VAB is a long arrow. That does not mean that A or B or anything is traveling a long distance. Like, I have no idea what kind of distance they're traveling. The space of that arrow does not represent a length in actual space. It represents a velocity. It's measured in meters per second. So what each of those arrows really means is, if you were to imagine a car or an object or whatever, sit at the dot of the tail of that arrow. If you were to imagine an object at a certain point in space at a certain time, a certain point in space at a certain point in time, that point being the tail of wherever the arrow is, then at that moment, the object would be instantaneously going very fast. Like, long arrow means at that moment, very fast. Short arrow means at that moment, very slow, right? Again, that's what the arrows now, that what velocity arrows now represent. Big arrows mean very fast in a moment. I have no idea how far the thing is going. When I put those triangles together, I'm not figuring out where somebody ended up. I'm ultimately figuring out how fast someone's going and in what direction. Like, that's what the triangle's trying to represent. And I guess I'm delaying, but the first line, Galileo's principle of relativity, form number 4, like where it says VAC equals VAB plus VBC, what it's trying to say, that we're now going to see in action in the computation, what it's trying to say is, when you add velocity vectors together, okay, it's a little bit more conceptually, you have to be a little bit more conceptually thoughtful than when you add displacements together. When you add displacements together, you're just accumulating like travels, right? If I walk here and then if I add this displacement vector to that displacement vector, I'm basically saying, well, if I walked that way and then I walked that way, like, how much did I walk in total? Like, it sort of is what it feels like it should be. But what does it mean to add two velocity vectors together? Well, I'll say what you cannot do. Well, what is meaningless? I could, like, throw a tennis ball across the room right now. I could throw a tennis ball across the screen, and I could also, like, throw a pencil at some other direction across the screen. Now, you could, and so each one has its own velocity, its own speed, and its own direction. You could, like, add those vectors together if you want, just to get, like, a new number. You could add the speed of the baseball relative to the lab plus the speed of the pencil relative to the lab. You could add them to get a number, but it wouldn't mean anything in the physical world. Like, would it, like, pencil plus baseball? Like, they have nothing to do with each other. It wouldn't mean anything. What we're trying to say with GPR4, form 4, and what you'll see if I eventually ever get to this problem that I'm over explaining already, when you add velocity vectors together, they have to be from different frames of reference. Velocity, this is all about that velocity is a relational quantity. It's not something that a object has, it's something that a object bears to another object, right? So what we're going to see in action here is you can't add the velocity of the baseball relative to the lab to the velocity of the pencil relative to the lab. That doesn't mean anything. What you can do is you can add the velocity of the pencil relative to the lab plus the velocity of the lab relative to relative to something else like a subway train. Or you can add the velocity of me relative to the Earth plus the velocity of Earth relative to the sun. And when you do that, what you get is the velocity of me relative to the sun. Or I'm going to say one last thing, and then I'm going to move on. Like the original example that people sort of understood in the video, but they did not understand like how it has to do with solving problems or whatever. The example I always say is like, you can add the velocity of me relative to a subway plus the velocity of the subway relative to New York City streets. And when you do that, what you get is the velocity of me relative to New York City streets. That's why I take subways, because I can stand still on the subway. Like I can not spend any energy. I can be zero velocity relative to a subway. But as long as the subway is going 80 miles an hour relative to Manhattan, then I am moving at 80 miles an hour relative to Manhattan, right? Duh. Like that's why people take subways. I'm saying now the amazing surprise is that concept applies even when none of the numbers is zero, even when there's negative numbers, even when the objects are not attached, like in an obvious way, like people are to subways, and even when there's two dimensions and all kind of angles involved. Velocity of one object relative to another plus another relative to a third gives you the velocity of the first relative to the third. That's what it means physically to add velocity vectors. That's what this picture is trying to tell you sort of right now, or this board. So enough of I thank you for indulging me. I'm now going to try to make this concrete by looking at the exam problem that I just screen shared. Page 6 of your practice exam is what I'm going to solve now. Okay, I'm sure I've lost everybody because I'm just like, blah, blah, blah. So here we go. I'm going to switch this screen. Sorry. No, sorry. Okay. And again, obviously, whatever I'm about to do right now, the whole point is like on your actual exam, you'll have a problem very similar to this one. Of course, details will be changed, but if you can do this one, that will help you a lot in the actual. Okay, part 3. All right, hold on. This is page 6. Okay. All right. So you're a boat traveling down a river, and it's telling you what the relative to the water, the riverbank has a constant speed of blah blah blah, and then relative to the riverbank, the boat has a constant. So we have like 3 objects here. So I'm going to draw a diagram first, obviously, but we have 3 objects: a water, a riverbank, and a boat, and we're given specific numbers for each one of them. All right, so we have, well, first of all, Okay. So first of all, this is just my rough sketch of the situation. It's already like kind of a, intense, complicated situation. But basically, we've got this stream, we've got water, we've got a river, right? We've got a river that's flowing in a certain direction. Water is flowing in a certain direction, and sorry. Yeah, let's do this actually. And so water's flowing in a certain direction, and then in the water, there's a boat that's moving at a certain speed in a certain direction. And it's all, so there's three different objects: river, riverbank, and boat. And each one of them is doing something totally separate velocity wise, right? This is a standard velocity addition problem. First, let me say, first of all, that you need three to add velocity vectors together at all. You need at least three objects because, again, remember, every velocity is a comparison between two. If you just had two objects, you would just have one velocity. There's nothing to add. You need at least three objects to add velocity vectors in a meaningful way. So this, what I just drew, is just a rough sketch of the situation, right? With no numbers or anything, just so I could picture that the idea that there's a river that's going some way past a bank, and then there's a boat doing something relative to that river. Now I'm going to be a little bit more specific in my drawing and try to put the numbers in and stuff as it says. So first of all, it says like the river bank is going at 45 degrees southeast at 3 meters per second. So I'm going to make a velocity vector here. Well, first of all, actually, I'm going to set up a little like let. Right. Just to be clear, I'm going to say let W stand for water. I'm going to say let B stand for river bank, which is to say like the shore, right? The ground. And let oh no, that's actually confusing. Sorry. I'll say I'll like say S, i.e. the shore. So W will stand for water. That's one object. That's one frame of reference. S will stand for shore. That is to say the riverbank, but I don't want to use the same letter twice. The riverbank, the shore, the land. Okay, that's what S will stand for. And then we'll let B stand for boat. Those are three different objects doing three different things. And that's three different perspectives. And the whole key to all of this Galileo stuff is each one of those perspectives is equally legitimate, like equally correct. The laws of physics are applying as correctly to the water as they are to the bank, as they are to the boat. Okay. So so now to draw the facts, it first tells me like that the riverbank is doing something relative to the water. The riverbank is going like, right? So the riverbank, the velocity of the riverbank, S. I know that's a little confusing. I'm sorry, but if I use R, it's really confusing because you'll think it's the river. So the velocity of, so for now I'm just going to say shore. Okay. I'm going to say like whenever I say shore, I mean riverbank, same thing, the land. Okay. The velocity of the shore, the land, relative to the water, according to the facts of this problem, is 3 meters per second at 45 degrees southeast. That's my velocity vector. The velocity, now notice again, we're talking about velocities now. Velocities are always relations. So every velocity that I'm writing now is two subscripts. What is it compared to what? So apparently the shore is moving relative to the river at 3 meters per second at a 45 degrees southeasternly angle. That's what the fact is. Now, you might say, I don't want to get myself to, you might, and you should put in the chat if you have an issue with this. That's just a velocity vector. It's showing a relationship of speed and direction between two objects. You might say, if you're trying to parse the words, you might say, wait, what? The shore is moving? What do you mean the shore is moving? Isn't the shore like sitting still? Isn't it a shore? What I'm trying to tell you, and what is a big thing in physics is, well, nothing is actually sitting still. Nothing is actually anything. The shore is sitting still relative to itself. The shore is sitting still relative to like planet Earth. It is stuck to planet Earth, but the water is flowing past planet Earth, right? Is flowing past the ground. And two things. Number one, that ground is not objectively stuck to the center of the universe. I'm not being technical here. I'm making a real point. Like the ground is on an Earth, and the Earth is moving past the sun at 65,000 miles per hour. The sun is moving past the center of the galaxy at 650,000 miles per hour, et cetera, et cetera. So there's nothing still about any ground. Now, I'm not trying to be technical nor confuse you. If you if you're thinking like, wait, I have to bring the sun into this, I have to bring like the galaxies into this. No, 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 you totally don't. But you have to recognize that since everything is in motion, and the motion of something totally depends on what you're comparing it to. The fact of the matter is, if water is going past a shore, then that's one way to look at it. You could be the shore looking at the water, say, you're moving past me, or you could just as legitimately be the water looking at the shore and saying, oh, you're moving past me. They're just like the sun can look at the earth or the earth can look at the sun. The laws of physics work the same way, and neither one is objectively correct. So we are told that the shore is moving past the water at 3 meters per second at 45 degrees southeast. Fine, that's fact number one that we're given. Then we're given another fact. We're given that the boat is moving relative to the shore at oh, did I just make that north? Sorry, I made that south. God, I made it southwest. It's supposed to be southeast. I'm sorry. Someone should correct me in the thing. Sorry, that's supposed to be south. All the facts I just said are the same, but I drew it wrong. It's supposed to go like this: southeast, southeast. So the velocity of the shore relative to the water is 3 meters per second at 45 degrees southeast. My apologies. I mean, I'm assuming down here that north is up on the page, south is down on the page, west is left on the page, and east is positive. Okay. So that's vector number one. Then the next vector it gives me, I mean, it tells us is it says the boat is now going northwest relative to the shore. I'm not changing this. I'm just making it a little shorter to make it. Okay, so the next one. Okay, so this is the next. So this is the velocity vector boat to shore. Notice, and technically, like this vector is supposed to be a lot longer than that, more than twice as long as the other. It's not really drawn very well to scale, but it's supposed to be a lot longer than the other one because it's because it represents something going a lot faster, 8 meters per second instead of 3. And it's going in a different direction. So this is now what the boat is doing relative to the shore. And the angle is less steep. It's 30 degrees instead of 45. Okay. Okay. So those are the facts that are given on the problem. Just looking at the chat. 1 second. Sorry. Okay. Nothing in the chat. You guys are okay? Okay. I know I'm being something. All right. So now we can start answering questions. So A, relative to the riverbank, in what direction is the water moving? So it is asking for the velocity. It's asking for just the direction of the velocity of what? Relative to riverbank, the water. It wants the water relative to the riverbank. So it wants water relative to shore. And it just wants the angle. Okay, how could I possibly know? Well, what I was given is the velocity. I wasn't told. Good. Thank God that someone's still with me. I mean, if I were you, I would not be with me anymore. I would have. But okay, Andy says set up a triangle. For sure, we are eventually going to set up a bit. It's all going to be about setting up triangles, like very soon, if I ever get to it. But for this one, right, this first question, I don't even think we need yet to set up a triangle, because if we look at it, like it's true, they're asking me a question that they haven't given. They didn't tell me. They're asking me about the velocity of water relative to shore. And it's true. They didn't tell me about the velocity of the water relative to shore, but they did tell me the velocity of the shore relative to the water, right? So even before I get into the triangles, and I totally agree with Annie, we're going to get into some major triangles here. For this one, I think the GDP that's going on here, like I think the concept that's going on, and again, people were asking about this like weeks ago. I think what we're trying to consider Galileo's principle of relativity, form number 4, the first case, the second case, case 2, the two object case. What I mean by that is, well, I'll remind you. Okay, I'll remind you. Galileo's principle of relativity, form number 4. Case 1, the one object case, is the velocity of any one object relative to itself is always 0, right? That's the one object case. According to relativity, if velocity is really a relation, not a property, if it's a relation between two objects, not a property of one, then the velocity of anything relative to itself is always 0, right? Nothing, like video games, like nothing is ever moving to itself. That's the one object case. The two object case is the velocity of one thing relative to another is always the opposite of the velocity of the other relative to the one. This is also the video game idea. Like, right? Like if the Earth sees the sun moving past it from east to west at 65,000 miles an hour, then the sun sees the Earth move past it in the opposite direction, west to east at 65,000 miles an hour. Or just like normal people, like if you see the subway go past you to uptown, that means if you're on the subway watching the person on the platform, they're moving downtown compared to you, right? Like, and the big thing that I'm saying, if you've ever noticed that ever, or if you realize that video games work on that principle, like, you know, if you switch from first person to third person and things switch and stuff, like or a movie, like if you've ever noticed that ever in life, what we're saying in physics is that's really true and it's universal and it's not an optical illusion. It's the nature of velocity. If I'm moving past you, then you're moving past me in the opposite direction, but at the same speed. Therefore, and that's what we're going to use right here. I'll also just remind you. So case 3 is the thing that we're ultimately using where we set up Annie's triangles. Case 3, the 3 object case, is that VAC equals VAB plus VBC. Now what I'm going to do here, remember A, B, and C in general are any random 3 objects. Call any 3 random objects A, B, and C. In this case, A, B, and C refer to the shore, the water, and the boat. Oh, wait, sorry, was that? So what I'm doing here is I'm saying, I'm talking a lot to show you the concepts. I mean, once you see what I'm doing, you'll see in a way it's simpler than I'm making it sound, maybe. I'm saying it's asking for what direction is the water going relative to the shore. I don't explicitly know that, but I know, I'm told that the shore is going at 45 degrees southeast relative to the water. That's got to mean that if you flip the vector in your mind, velocity of shore relative to water means what the water sees the shore doing. It means if you get in the perspective of the water, if you are like a lily pad floating in the water, and the water is still to you, then you see the shore going 3 meters per second at 45 degrees southeast. Therefore, okay, what I'm saying, and this is so I'm saying, if the shore sees the, sorry, if the water sees the shore going southeast, then I'm flipping, but like the opposite of south is north, and the opposite of east is west. Like, so if the shore is seeing the water, sorry, if the water is seeing the shore go southeast, then the shore must see the water go northwest. And that's why my original diagram, I mean, that's why my original picture looks like this. Like the river is going like that, northwest, from the perspective of the shore. If I drew the shore from the perspective of the river, it'd be the opposite of that. I don't know if that, so that's the answer to that one. I'm going to keep going. Unless you, I mean, you put questions in the chat, but I know that the hard part is the triangle part that Annie's anticipating. So I certainly do want to get to that. But that's, and so this was so that was step 4. Okay. So that's that one. Okay, so I'm going to go to the next one now. So, and this is often true on these exams. Like when you don't know what's going on, or when you're still studying or whatever, like it all looks like, it may all be very intimidating and all look complicated and all annoying. As you get more and more used to it, there is a pattern where usually the early questions, you have one big setup, one big problem, and the early questions in that problem are usually like they're not supposed to be trick questions. They usually are somewhat straightforward and fast. They're meant to be guiding your thought process, they're asking you to put together pieces that you're going to need toward the end of the problem to put all together and answer one big thing that the whole problem is driving at. Okay, so one quick thing I'm just saying from a test taking point of view, if after I know I'm spending all this time trying to explain it, but in the end of the day, the answer I'm saying to A is pretty fast answer, and the work you could do it in your head once you get it. It's not a lot of work. That's not unusual, and it's not a trick question. We're just trying to get the concepts laid out to then put everything together in the later parts of the problem. So, for example, part B now, I'll try to go a little faster now. Part B, well, similar thing. It says relative to the boat, how fast is the riverbank going? Like, what is the speed of the shore relative to the boat? Now, this time it doesn't want the angle, like it wants the magnitude, just the magnitude. Right, that's the question, right? And by the way, I can say C diagram above. I'm going to stop writing in the steps on the right. I think you can get that now. But step 1, I could say C diagram above. Step 2, what's the question? The question is what is the magnitude of VSB? Like what is the speed of the shore relative to the boat? Okay, now how could I know it? Well, I don't know it explicitly, but I was told that VBS equals 8 meters per second. I'm told that the boat is going 8 meters per second relative to the shore. This is, again, the same concept. I know, like, VSB must equal the negative of VBS, the opposite of it. But opposite means in direction. They're not asking me, so it's got to be the same number, but in the opposite direction. They're not asking me about direction this time. They're only asking me about the number. So it's got to be the same number, i.e., if, okay, so, i.e., if the boat travels or moves, whatever, at 8 meters per second relative to the shore, then necessarily the shore is moving at 8 meters per second relative to the boat, just in the opposite direction. But this time it's not asking about direction, right? It's just, so this is just trying to break down, do you understand how velocity works? This is all GPR, form number 4. Then the boat travels, then the shore travels at 8 meters per second relative to the boat. So I'm saying the answer is, I'll just put it up here. So VSB we're looking for is 8 meters per second. That is the answer. Okay. Again, once you get it, it's not that, I don't know what. C, similar thing. I'm just going to keep going. I mean, obviously, what we have to get to is the big computation. C, from the water's frame of reference, at what velocity is the water moving? That's like saying, what is the velocity of the water relative to the water? In fact, what you might want to put in your notes, I'll put it here. It's like, hold on. Okay, just to be clear before I move on, any of these terms, relative to, compared to, in the frame of reference of, in the reference frame of, according to, as measured by, all of those mean the same thing. And they're all what we're trying to say. If we say VAB, for A and B are any two objects, or in this case, VBS or VSB or whatever, we mean velocity of A relative to B. And the order does matter. We're saying the order does matter. A relative to B is the opposite of B relative to A. What does this all mean? Like, it means assume, if you say VAB ever in any of this notation, you're saying velocity of A relative to B. And what that really means is it's assuming that B is still. And it's like looking at it from B's perspective. B regards itself as stationary and is watching as A moves past it. It's first person perspective, like in a video game. I'm not saying that's easy. I'm saying it's super important. And we're now doing calculations based on that. It may take a while for it to sink. Like, don't underestimate it. I'm yelling because I get excited or because it's intense. I'm not saying this is, I'm saying you all have experience with this, but you really do, especially if you play video games. Like, and I'm not saying you should, whatever. But what you don't necessarily know until you take physics is like how real of a scientific idea it is. It's not an optical illusion, and it's not only sort of sometimes true. It's the nature of motion. So I'm saying whenever you get into the perspective of an object, that means you're regarding that object as stationary and watching the world go by it. And you can do that and do that all the time in physics. So anyway, therefore, in this question, where it says, see, so that's just like a reminder, that's just like instructor sidebar or whatever. But so now if C, and again, I'm not like writing out the steps anywhere. I just want to give you, because I want to get to the heart of this matter and give you the practice. But C, if it says, what's the velocity of the water relative to the water, it's asking what's the velocity of the water relative to the water. Well, the whole point is that the velocity of anything relative to itself is always zero. That's what we mean by VAA equals zero. It doesn't matter what A is. Whatever it is, relative to itself, it's zero. I can't emphasize that enough. So the answer is VWW equals zero. Like, okay, and so, okay, I don't know what more to say, but now finally, okay, we have 25 minutes. So we're going to get to Annie's thing now. I mean, to get to the whole heart of the matter. D now is asking, and I might not get to E today, and that's okay. But the main thing here, like the most work you have to do, and I'm going to warn you right now too. I mean, I've been like trying. This is the heart of the matter here. D is the heart of the issue. It's where you have to do the most work to get an answer. You can't do it in your head. I can't do it in my head. I mean, like the answer is not some obvious thing. You're technically adding vectors together, two vectors together to get a third, but it's not arithmetic. Like if one vector is 8 and the other is 5, you're not just adding them and getting 13. You're getting numbers that require the same kind of chart and diagrams and triangles that we did 2 days ago. I mean, that we did last week. Okay, and that Andy is anticipating. So take this part seriously. This is where the most points are to be gained in the exam. Yeah, 10 points total, 12 points. Yeah. And where I would look the most carefully for all your steps and everything. So, okay. So first of all, so what we want to know here, and if you can do this, you can do anything related to it. So we want to know the velocity of the water relative to the boat. That is the question. What is the velocity of the water relative to the boat? In fact, specifically, the velocity, which means we ultimately want to get how fast the water is going relative to the boat and in what direction. So we're asking someone in the boat is sitting there in the boat. And if they look at themselves, right, or they look at the boat's not moving away from them. And if they have a neighbor in the boat, like two of you are sitting in the boat, you're not moving relative to each other. You're in the boat, right? You're watching water flow by you. So we're asking, in what direction is that water flowing by you and at what speed? And that's what we're about to figure out here. Now, it's totally not a given. Right, what's given, if you go back to the original diagram, okay. What's given is SW and BS. And whenever I put these arrows above something, I'm meaning to highlight it's a vector quantity. It means that it includes magnitude and direction. Okay. So I'm given shore relative to water, and I'm giving boat relative to shore. And I'm asked, what's the water doing relative to the boat? So this is velocity addition. So the first question is, what vectors do you add together to make the third vector that you're looking for? This is to know like this is where the case 3, the complicated case of GPR4 comes in. Like VAB plus VBC equals VAC. Whatever A, B, and C stand for. The velocity of me relative to the subway plus the velocity of the subway relative to the platform gives the velocity of me relative to the platform. That's the concept that you need to know to do this, to know which ones are we adding to which to make what. So you have to follow the pattern of those letters. You have to arrange the frames of reference in that way. So in other words, if I want to know velocity WB, then what I'd have to add together if I want to get the velocity WB, which is what the problem is asking for, I would have to add together velocities such as WS plus SB. Like, where did I get that from? From the pattern AB plus BC equals AC. It's trying to tell you that whatever objects or letters you use, you have to arrange them that way if you want to add things. Again, it's not, don't just memorize it like the law of transitivity or something. If you go back in your minds and think of a simple case of you on a subway or an escalator or whatever, that's the concept we're saying. U relative to the escalator plus the escalator relative to the mall equals U relative to the mall. That's why you take escalators. And it even works if you go backwards, like if you're walking up the down escalator, so you put in minus signs, it's still true, right? So you have to, when you're adding velocity vectors, you have to arrange the frames of reference that way. So here's one way. I'm saying, for example, like this is what I'm going to do. If I want WB, one way I could arrange things in terms of things that I know is I could add WS to SB. Hold on, I'm just looking. Someone's coming in. Is there anything in the chat? Oh, is it? Oh, good. Annie, sorry. I just saw what Annie wrote like a million years ago about the other problem, but sorry, she's totally right. Yay, Annie, and submit for points, please. Thank you. Okay. So now, VW. So we're going to add together. First, I'm going to make a triangle. So first I'm going to do graphical representation as it asks. Graphical represent. I don't mean we're going to write a graphic novel. I just mean like VWS. Right. So, let me see if I can do this quickly. So VW, right, was, so these, okay. Sorry. No. Yes. Yes. Okay. So VWS was 3 meters per second at 45 degrees northwest, right? That was V. And VSB was southeast, right? Was longer and southeast. Let me just move this over. Sorry. I'm just going to move this over. And so then VSB, we said was like 8 meters per second at 30 degrees to the southeast, right? So those two vectors, and I got those from previous answers. Those two vectors are being added together, right? Tip to tail. So I'm adding the 3 to an 8, but I'm adding them tip to tail in these funky directions. So the answer I'm looking for, what I'm ultimately going to get is the vector that completes the triangle. That the red thing is VWB equals the answer. So if my diagram is at all drawn to scale, which it kind of is not, but if it's at all accurate, the ultimate answer I get should be, pointing off to the northeast as this triangle represents. But this is just a rough representation of the kind of answer I'm looking for. How do I actually get the numbers in the next 15 minutes that we have? Sorry. So number one, that's like the first triangle that maybe Annie had in mind. Like that's a triangle that represents the whole situation. I'm adding two velocity vectors together. I'm getting a third. But now how do I actually do it? I'm going to draw a bunch of triangles. Well, I'm going to do the exact same thing that we did with the displacement vectors, but I'm doing the same math. It's just what it means now conceptually is velocities rather than displacements. So we're going to use the component method like we did last Wednesday. And we're going to zoom in on each individual vector. We're going to treat each individual vector as the hypotenuse of its own individual right triangle. In other words, this is now GPR5. We're saying every two-dimensional situation is really two one-dimensional situations occurring at the same time, but independently. So I'm going to zoom in, right? I'm going to zoom in on that. So now I'm going to break this whole triangle apart. Like I'm going to actually analyze it. So first I'm going to take that yellow vector, VWS. Because it is yellow already. I'm zooming in on just it. So it was VWS equals 3 meters per second. I'm going to get its components. To go northwest is really to go some amount west plus some amount north, right? Tip to tail. See what I'm like, right? I'm getting its individual components. I'm making it into a right triangle. Again, notice, and this goes back to, sorry, again, okay, Annie said, like if you looked at this first triangle, you might start wanting to do things like law of cosines. And I'm not saying you can't, but I'm saying it's not going to work out consistently the way you might like. And it's also not going to show you physically what's happening. So that first diagram just like represents the whole situation in general. But now I take in other words, that triangle is not a right triangle. But now I turn it into individual right triangles. I say that to go northwest is really to go some amount west and some amount north. And if this angle was 45 degrees, I believe it was, then this side here, VWSX, like how much I'm going to the left is 3 cosine 45. And this amount over here, VWSY is 3 sine 45 because opposite is cosine of the angle is opposite over hypotenuse and cosine is adjacent over the hypotenuse, right? And those are numbers that you can do on your calculator. So this is like 2.12, and this is like 2.12. It's the same because 45 degrees has the same cosine. All right, so I just broke up that triangle. Now the other triangle, the other vector, sorry. The other vector is the big blue one. This one is 30 degrees. This one is velocity of shore relative to boat, and it's longer because it's going faster at that moment, 8 meters per second. So we break this up into its components. To go northeast is really to go some amount east and some amount north. Notice I always say it like that. That may seem a little jostling to you. What I always do, my huge recommendation to you, I'll just say this fast. It's a huge important strategy. If you're still listening to me, it's definitely a pro tip. Like whenever you draw a vector and then you break it up into components, what I always recommend, well, first of all, I just recommend practicing this because as fast as I'm going or not, or whatever, like when I drawing these things, I'm making it seem as straightforward as I can. But every one of these triangles I'm drawing and breaking up, there's you have to practice on your own because there's more than one choice. I'm making the correct choice, but there's other choices you could make that would be incorrect. And what I'm trying to say is, whenever you break a vector into its component parts, my recommendation is always draw the horizontal first, and then from the tip of the horizontal, draw the tail of the vertical. Just trust me. I mean, do whatever you want, but especially if you have limited time to practice, notice that I'm always drawing the horizontal first and tip to tail. From its tip, I draw the vertical. That way, all the angles I'm getting and all the directions I'm getting are all things like south of east or north of west. I'm always measuring tacitly relative to a horizontal, so it makes it all work out. That's just a pro tip. Like, anyway, but that's why I say when you go northeast, you're going some amount east plus some amount north. I mean, it's also true that you're going some amount north and some amount east, but that's not as wise to draw it like that. Anyway, so we've got, so VSBX, like how much east are we going, is 8 cosine 30. And VSBY is 8 sine 30. 8 cosine 30 is a number. It's the number 4. And 8 sine 30 is a number. Oh, sorry. No, oh my God. No, 8 sine 30 is the number 4. Sorry. And 8 cosine 30, I'm losing my mind, is the number 6.93. And what do those numbers represent? They're legs of the triangle. But notice, you got to have arrows and you got to have all your units and notation because these are not how far anybody went. Nobody went this far. These are velocities. What we're saying here is that if you go 8 meters per second at 30 degrees to the southeast, what you're really doing is going 4 meters per second to the south while you go at a rate of, so you're really going 4 meters per second to the south at that moment, while you had 6.93 meters per second to the east. We're talking about your instantaneous velocity components. Now, of course, we've got 8 minutes. What am I doing with all this information? Now I'm going to put it together in an XY chart. I'm going to say, okay, so like every two-dimensional problem is really two one-dimensional problems happening at the same time independently. In other words, I'm adding now VWS to VSB, but I'm adding it in each one dimension at a time. I'm going to fill in the numbers in this chart from what I just got from my triangles. So the X component of VWS is 2.12, right? But it's going to the left. It's going west. So I put that in as a negative. And the Y component of VWS was also 2.12, but it's going north, up on the page. So I leave that as a positive. And VSB, the X component of VSB is 6.93. It's going east, it's going right. That's a positive. And VSB, the Y component, how far am I going, north or south? Well, I'm going 4 meters per second according to this triangle, but it's south, it's down the page, it's negative. So I go like this. So I put these 4 numbers in my chart, and I'm adding them together because this is velocity addition. Because we said from the start, we're trying to get the answer. We're almost done with at least this part, and that's where we'll stop. We're trying to get VWB. We believe that VWB is VWS plus VSB, right? But we're adding the numbers in one dimension at a time. So negative 2.2 plus positive 6.93 gets positive 4.81, and and positive 2.12 minus 4 is negative 1.88. So what does that mean? It means I can draw my final triangle to get my final answer. It means at the end of the day, after all this addition, at any given one moment, what the water is doing relative to the boat, at any given one moment, the water is going 4.88 meters per second to the east, while at the same time, it's going 4.88, approximately 4.88 meters per second to the east, while at the same time, it is also going 1 point whatever 88 meters per second to the south, right? At any given one moment, we have 4 minutes left. What the water is doing is going a certain amount to the east from the perspective of the boat, while it's going a certain amount to the south from the perspective of the boat. So on the whole, what the water is doing from the perspective of the boat is going at a certain overall speed and a certain overall angle. What's the overall speed? Well, the VWB must equal the square root of the squares of VWBX, right? Pythagorean theorem, in other words. So that's so VWB equals approximately 5.16 meters per second. That's the speed. The water is going approximately 5.16 meters per second relative to the boat. And the angle, I'll just put it up here so you have it on one page. The angle, how do you get the angle? Well, the angle must be the arctan of 1.88 over 4.81. Why arc? Because tangent of angle equals opposite over adjacent. So we don't want the tangent, we want the angle itself. So the angle equals the inverse of the tangent. What do you do in your calculator? So it's approximately 21.3 degrees. In what direction? Well, just looking at my picture, if I've been careful about all my arrows going in correct specific directions, if these are not, and this is something I definitely do take points off on the exam, like you're not just drawing triangles. It's not a geometry problem. It's a physics problem. So you're not just drawing triangles. You're putting together vectors into triangles. Every line has a tip or a tail. It's all vectors. So you can see the direction. So I can see from this final diagram, aha, the final vector points somewhat to the east and somewhat south. It points southeast. In other words, this final direction is 21.3 degrees southeast. So my final answer is that the speed is approximately 5.16 meters per second. The direction is approximately 21.3 degrees southeast. Notice in my original sketch, which was very sketchy, notice my sketch was so sketchy. Okay, that looked okay. So if I were doing this in an exam right now, I'd look and I'd say, wait, something's either my sketch is too sketchy or my answer's wrong. I think my sketch is too sketchy. In other words, this just should have been, is this a slight adjustment? That this should have been much longer. So that the final thing is going to the southeast. Okay, I'm doing this way too fast. But we have 1 minute left. But this is the answer. I'm not correct. I'm not changing the answer. I'm just trying to make this clear. It's not that clear. But anyway, the final answer is this right here. And it is the answer to the question. And this is the end of class, but this is the answer to the question from the perspective of the boat. What is the water doing? In other words, what is the water doing relative to the boat? It's doing this. That is the answer. And that's the hardest. If you can do that, I mean, you have to let it sink in and you have to practice.
Which question is this again? Sorry.
Oh, sorry. It's the one that's on the screen. Hold on. Wait, it's what says all on the front if you look at the notes, but it's from the practice exam. It's page 6 of the practice exam. It's this right here. It's
the practice. Okay.
Yeah. So and I think and I know class is over, but to everybody, it's hard. I'm not saying this is easy, and I did go fast, but it's among the harder things in the exam. If that's why I went over it today. If you can follow this or practice on your own, then you're doing one of the harder things on the exam, and then the other stuff is comparatively easier. But anyway, we'll talk more on Wednesday. But yeah, that's what this was. That was that problem. This problem, page 6, part 3. And it was specifically part D, which is the meat of the problem. So okay, but that's class. Thank you all. Been very patient. I know that was a lot. See you in 2 days.
Bye, Professor.
Oh, thank you. Bye. Thank you. Bye.
Professor, I have some questions.
Yes. Okay. Hang on one second. Let me turn off the recording for happy to.